All right, so just to continue from our last lecture, we talked about the moment generating function, right? So the moment generating function is actually defined as the expectation. It's defined as expectation of a transformed random variable x. And the transformation is the exponential function of t times x. And here t is a real value. And we also only consider real valued x here. So basically here, the random variable is a scalar. It's not a vector, but we'll see actually two random variables together very soon. So in that case, the moment generating function can be defined for more than one dimensions random variable. We call that random vector. But for now, it's just one dimension. X is scalar and t is also scalar. So basically, when we say a moment generating function, it is a function of t, okay? Make sure the argument is t, and t is a real value. When we vary t, then the corresponding moment generating function value will vary. So why do we say it's moment generating? The reason is that once you obtain the function, and if the function is differentiable at 0, so and also has, I would say, smooth enough, so it has many derivatives at 0, then each derivative at 0 will give us the moment of the corresponding order of x. So like the first derivative at 0 give me the first moment, second derivative at 0 give me the second moment, and so on. So that's why we say it's moment generating. And also, if you think about the calculation, if you are able to derive the moment generating function, then you save some computation from, say, computing the first moment, second moment, third moment individually. Because if you think about each moment as an expectation, right? For discrete random variable x, the expectation will be computed by a sum. For a continuous random variable, the expectation will be computed by integration. So if you calculate moments individually, then each moment will require one sum or integration. But if you are able to calculate the moment generating function, then you just need to do the sum or integration for once. And then what's left for you is just differentiation. Okay, so this is the quick review of what we did last time. And last time we first showed an example about calculating the moment generating function of a binomial random variable. That's the first example. And the second example we didn't finish, it's about moment generating function of the Poisson, of a Poisson random variable. So just bear in mind that to compute the moment generating function, because it is an expectation, you need the probability mass function or the probability density function, depending on whether the random variable being discrete or continuous. So here we will use the probability mass function because Poisson variable is discrete. Okay, so to do the computation, we just plug in this this probability mass function here. So essentially, you see, if I copy it down here, times lambda to the power x times exponential negative lambda divided by x factorial. Then what's left for me is to simplify the sum. It's a sum of infinite series. So how do I simplify it? To do that, recall the last time I said, we will make use of this property. Okay, so for any lambda positive, we actually have this property from the fact that the probability mass function would sum up to 1 across all the possible values of my random variable. The random variable can take values from 0, 1, 2, up to infinity, all positive or all non-negative integer values. They will sum up to 1. So to simplify this, I will try to create a form of this so I can simplify the sum. So how do I do it, right? So the most straightforward way to think about it is to combine similar terms. So which terms are similar? This one has x in the power. This one also has x in the power. So it's straightforward that we should combine them, right? So if I combine them, let's take a look. I just So e to the tx times lambda to the x will give me e to the t times lambda, their product, to the power x. Okay, and I didn't do anything else. I just put down the remaining terms. But in order to simplify it, you see what I need here. So here you see in the sum here, I have lambda and the lambda. Lambda appears in two places. So in order to create a sum like this, I also need to put the base here below x, right? This e to the t times lambda to the exponential term. That's what I need. So I can create a term like this. So how about I just create a term I want by writing, say, et times lambda to the power x times exponential to the negative e to the t times lambda, x factorial. So this is how I created the term I need, so I can have a sum of 1 here. But I need to make up for what I introduced, right? So I need to just create a canceling term. So I can just multiply exponential to the e to the t times lambda. So this term and the term I introduced will cancel each other, give me 1 times what I left here, e to the negative lambda. So therefore, you can see that what I'm having here is I created a term here so I can simplify the sum. So basically, this term would be equal to 1. And these two terms has nothing to do with x, so I can get it out of the sum. So basically, after the simplification, what I have here is just exponential to the et lambda times e to the negative lambda. That's it. And if I want to do one further simplification, it's just exponential to the lambda times et minus 1. I just combine those two terms, and that's it. So this is the moment generating function I have for Poisson x. Then let's try to check whether the moments match. So I know for Poisson as a special distribution that expectation of x, the first moment, is equal to lambda. That's what I know. And I also know the variance of x is equal to lambda. So Poisson is special for having both the expectation, the mean, and the variance equal to the parameter, the rate parameter lambda. So in this case, based on what I said last time, for the second moment, we have this interesting relationship with the mean and the variance, right? So it's equal to the mean square plus the variance. That gave me the second moment. So what is it? You see, it's basically lambda squared plus lambda. That's my second moment. Now let's verify if the moment generating function we just derived will give me the same result. So let's take a look at the derivative. First derivative at t, what is it? So clearly, we will use the chain rule again to do the derivative, right? So this stays, and then I will do the derivative in the power. That will give me lambda e to the t. Okay, then evaluate this derivative at 0, t equals 0. What is it? So when t is 0, it's 1 minus 1, that's 0. E to the 0 is 1. And here I have lambda times e to the 0, so I get lambda. That's the first moment, and it agrees with my knowledge. Now let's do a second derivative again. So now we have t in two places, so we will try to use the rule again. So first take derivative against t for the first term, keep the second term unchanged, plus keep the first term unchanged and derivative on the second term. So let's do it. So e to the lambda et minus 1 times lambda et. Okay, that's what I have for the derivative here. Second term stays, so I just put it down. Okay, And second term is I keep the first term unchanged. And for the second term, I take derivative. It's just itself. That's it. Okay, now let's evaluate the second derivative at t equals 0. So let's see what we have. T equals 0, this term is 1, this term is lambda, this term is lambda. So I have lambda squared. And second term here, when t is 0, I have lambda. So you see, it agrees perfectly with what I derived based on my knowledge. So again, this example confirmed that the moment generating function indeed gives me the correct moments. Okay, that's the puzzle. So we have shown you 2 examples for deriving the moment generating function for discrete random variables. Now we are going to give you 2 more examples for continuous random variables. So I call this example 3. Before I move on, do we have any questions so far? Okay, great. So yeah, thank you for giving me some feedback from the camera. So for the third example, we will have this continuous random variable exponential distribution. Okay, so we know for exponential distribution, this parameter lambda must be positive, just as the lambda in Poisson. Okay, and what's the probability density function? So here, you know, for exponential random variable, x is positive. Its domain is the positive part of the real line. So the probability density function, I write PDF and use this notation small fx. It takes this form as lambda times exponential to the negative lambda x for x positive. Okay, and for how about the negative part? So for x negative, actually, I should say, it's actually equal to 0. So the exponential function density have 0 in the negative part of the real line. Density has 0, but for the positive part, that's it. Okay, so then let's calculate the moment generating function using the definition as the expectation of e to the tx. Okay, now we're going to use the expectation for a continuous random variable, which is I do the integration over the domain that's from 0 to positive infinity, e to the tx. And here the small x means that any value my random variable may pick from the domain times the density at that value x dx. Okay, so now I put into the density function. So here, again, the question is how do we simplify this integration? Just as in the first 2 examples, we need to simplify the sum so we can get a clean form for the moment generating function. So to do that, let's look at the density and use the fact that the density would integrate to 1. This is the fact we will use. And this is conditional on the condition that lambda being positive. Okay, so for any lambda positive, we have this fact. And we are going to use this fact to help us simplify this moment generating function down here. Let's do it. So you see e to the tx times lambda times e to the negative lambda x dx. Again, we will try to combine similar terms. Here, obviously, the 2 exponential terms are similar. If I combine them, I would have the power being the sum, right? And still an exponential term. So I put a constant to the front, lambda. For the 2 exponential terms, I would have, you know, t minus lambda times x. But you know, I want to create a term like this. So I want to have a negative sign in my exponential function. So I prefer to write as negative lambda minus t times x dx. Okay. So in order to simplify this term, you see, how do I do it? Again, I want to create a term like this. in order to solve this integration, here the lambda and this lambda must be the same. And also this lambda must be positive. So therefore, let's do it. So how about, let me say, I assume for simplicity for now that lambda minus t is positive, okay? So if this holds, that means t is less than lambda. And to me, that's okay because, you know, to evaluate the moment, I only need the t at 0, around 0. And here lambda is positive. So t less than lambda doesn't exclude the fact that t can be 0. So therefore, under this condition, what I can do, you know, is to write this. I create a term here, lambda minus t times exponential negative lambda minus tx. So this is the form I need here to simplify it. But to restore the original form, what I can do is to multiply this factor lambda divided by lambda minus t. So you see this lambda minus t and the denominator can cancel each other. So this term is equal to this term I have here and dx. And why this will work is because this ratio I created, lambda over lambda minus t, first is positive because lambda minus t is positive. And this has nothing to do with x. So I can get it out of the integration. And for what's left in the integration, it's equal to 1. Okay, so then I have this as equal to lambda over lambda minus t. But please be sure to write that here, this moment generating function, this one is actually holding for the t less than lambda. So because otherwise, if t is not less than lambda, this is not positive, then we cannot use this fact to simplify the integration. So yeah, so make sure here the moment generating function we derive is for this t under this constraint. Okay, but as I said, if we just want to know the derivative of moment generating function at t equals 0, it's okay because lambda here is positive. Does that make sense? Okay, so for this, I will just leave it for you to check that this moment generating function still give me the correct moments. So just take this as an exercise. So check that the mx first derivative of 0 is equal to first moment, and this is equal to second moment. So use this as an exercise to check it yourself. All right, that's the third example, exponential distribution, which is a common distribution, common continuous distribution. Lastly, let's look at normal distribution, the most common continuous distribution. So now let's assume x follows standard normal distribution. Okay, so now I'm just going to be quick. So the density PDF is fx equals 1 over root 2 pi exponential to the x squared over 2. Okay, and here the x can be any real values from negative infinity to positive infinity. So if there's one density function I hope everybody can remember, it will be this one because we use normal distribution so often. So it's good to know the form. Okay, so let's look at the moment generating function, mx at t, and t is also a real value. So let's do the integration here because the domain for x is from negative infinity to positive infinity. We do the integration and here the density is here. So I'll just put it in, saving one step. So 1 over root 2 pi. Okay, that's the integration. Again, how to simplify it, right? That's always the question. To simplify it, again, we'll use the fact that the density function integrates to 1. So the fact here is from this negative infinity to positive infinity, 1 over root 2 pi exponential to the negative x squared over 2 dx is equal to 1. we will use this fact to help us simplify it. And looking at this term, how do we simplify it? You know, this fact requires that we have a square term, negative square term in the exponential function. And here you see what we have. Let me just put it. So this root 1 over root 2 pi doesn't matter. I just leave it here. What we're concerned is the exponential term, right? So if I put it to combine the two terms, I would have, you see, x squared over 2 right here. Here, because I put a negative sign here, so the tx will become negative tx. Okay. Then this is a mathematical question. How can I make this term into a square term of x? And you see what we can do. Let me just put it here. So how the question is how to make x squared over 2 minus tx a square equal to, let me say, something like x minus something square over 2, because I need this form, and maybe plus something. So I will create a term like this so that I can use this fact. So to make this form a square term, we can do this, you see. So for the left-hand side, let's just put 2 in the denominator because the form requires a 2 in the denominator. So, you know, in the numerator, I have x squared minus 2tx. So now the form should be familiar to us somehow because we know, think about what is the x minus t squared. We should be familiar with this. Once we expand this, it actually gives us x squared minus 2tx plus t squared, right? So therefore, I'm just lacking the t squared term here. Otherwise, I already have a square. So therefore, for this, what I can do is that I can add t squared and minus t squared so that I can create a square term, x minus t squared here, minus t squared over 2. So you see, this is what I can do here. Once I apply this fact to here to the moment generating function, I would have 1 over root 2 pi exponential. Remember, what I'm discussing here has nothing to do with the negative sign. I'm just talking about this part. So I carry the negative sign and I have 2 x minus t squared here and minus t squared over 2 dx. Okay, so I'll pause here a little bit so you can take a close look about the algebra I applied. What I did basically is to create a square term about x. Then I'm almost there because, you know, for this integration, it applies to x, right? And here I'm just shifting x by t. But because the range of x is from negative infinity to positive infinity, so that's the same range for x minus t, for any t. So that's why I can still apply this result to here to solve the integration. So what I'm saying here is that this term, additional term here, has nothing to do with x. So I can just safely move it out of the integration. So what I'm having here is that this negative, they cancel. So I have e to the t squared over 2 out, okay? And what's left inside in the integral is 1 over root 2 pi exponential to the power x minus t squared over 2 dx. And as I'm saying here, the dx is the same as, you know, I can write this dx as dx minus t. It doesn't matter because here shifting by t doesn't change the range. So it's still the same integral. And for the second part, this, because of the box here, I know it's equal to 1. So I simplified it. And the moment generating function is simply exponential t squared over 2. So I would say that this moment generating function is the thing I hope everybody can remember, because I think this is a very simple form and we will use this result again. So basically, looking at this interesting result, the density function of a standard normal variable has this exponential term negative x squared over 2. And this is just a normalization factor. Okay, this is the key part. And the moment generating function, now you see the variable is not x, but t, right? And it still has this exponential t squared over 2 form, but no negative sign in the power compared to here. So you see, this is something like a very interesting mirror, right? One has the negative sign, one doesn't have it, but both are very simple forms. Okay, so the reason I say this is very important is because the next thing I want to say about the importance of a moment generating function is that it uniquely determines a distribution. How do we know that dx equals dx minus t? This is a fact in calculus. So because you are just shifting, so basically x is the variable you want to integrate, right? And you're shifting it by just t, a constant t. So therefore, when you do the differentiation, it's the same. So I don't know if this is a good explanation, but so for me, it's just, so I'm just trying to add more. This is from calculus. So basically, we can know like dx is equal to dx minus t, like t is a constant, right? And we also know dx squared is 2 times dx. So something like those. So that's what I mean. But if you don't want to look at this perspective, it's still okay. What I'm saying here, or maybe let's do this. So I'll just go one more step. Okay, so probably this is a better explanation. Negative infinity to positive infinity, 1 over root 2 pi exponential to the power x minus t squared over 2 dx. Let's formally do a change of variable. Let's say that I define y equals x minus t. Okay, and then once I do change of variable, I will do integration for y instead of x. And the range, x goes from negative infinity to positive infinity. So for y, its range is still negative infinity to positive infinity, because no matter what t is, there's nothing we can do with the real line, still the real line, right? So I have this y squared over 2. And then now I'm going to use the fact that dy equals dx, so dy. So this is just the same form as the box I have here. So this is equal to 1. Does that make sense to everyone? Okay, sounds good. All right, so yeah, I think so basically for the prerequisite of this class is, I would say we don't use, at least I would not try to use multivariate calculus as much as possible, but I think univariate calculus will be something we use very frequently. So it's very nice to get a review if you forget some of those facts. Okay, so I'll just continue. So why is moment generating function so important, right? The reason is that we can use the moment generating function to tell a distribution. So for example, let me just give you one property next, and we will see how this can be very useful. All right, so let's say that there are 2 important properties about moment generating function. The first one is that if you apply a linear transformation of your random variable by multiplying it with a constant and adding a constant to it, then the moment generating function can be directly transformed. So you don't need to derive the moment generating function for the transform variable from scratch. You could directly just apply the original moment generating function and to obtain the transform variables MGF. So specifically, let's say that if x has MGF mx, Okay, so this is the function for it. Let's say that t, I still use the t as the argument, just to be clear. And I define y to be a plus bx, just a transformation, linear transformation. And a and b are any real numbers. Okay, so then the property is that then y has MGF of this form. I call this my. So put the random variable in the subscript, myt equal to exponential to the power at times mx bt. So you see, I directly apply my known MGF for x, put it here, just change the argument from t to bt times this constant e to the at outside. So that means if we just apply a linear transformation to a random variable, we could use our existing MGF, and there's no need to derive the MGF for the new variable from scratch. And the proof for this is very straightforward. We just apply the definition of MGF. So I'll write it. So MYT, right? It's defined as expectation of exponential TY. By the definition. And now I'm going to use the relationship between y and x. T times a plus bx. Okay. And now I can write this as a product. E to the first term is at times exponential to the btx. Okay, so an important fact about expectation is that we can move any factors unrelated to the random variable outside of expectation. Here again, the random variable is x. So this e to the at is not random, it's just a constant factor. We move it outside. So it's e to the at times expectation, exponential btx. So you see, I put a parenthesis around bt because these are just a constant times x. And in my definition of moment generating function, you see the t is the thing that multiplies the random variable in the exponent. So here it's bt, not b, not t anymore. So then by definition, you know, this is exactly just mx bt, right? It is the moment generating function applied to the constant multiplies x. So that concludes the proof. So it's equal to e to the at times mx bt. Right, so this property says that for this linear transformation, let's call this b a slope and a an intercept. So for the moment generating function, you just put the slope inside the MGF and you put the intercept in this exponential form outside of the moment generating function. So with this property, you see, we can actually derive the moment generating function for any normal variable, not necessarily standard normal. So we can make the mean be general, not zero, but mu, and the variance be general, not just one, but sigma square. And then we can still directly apply the moment generating function here. Let's do it. Okay, so let's see in this example. Let's say that we have this general normal random variable with mean mu, variance sigma square. Maybe I'll just make it y, okay? Not to be confused with the x we have before. So what's this moment generating function? This is a very important fact we want to know about the normal variables. So note that we can write the random variable y as equal to mu plus sigma x, where x is the standard normal random variable. So in other words, for any normal variable, we can create it from a standard normal variable. Just multiply the x, the standard normal x, by the standard deviation and add the mean mu. So then the resulting random variable y is following this normal distribution with mean mu and variance sigma square. Does it make sense to everybody? So the reason is that the standard deviation you can consider as kind of like a stretch, right? So you make it the distribution either more narrow or broader by making sigma smaller than 1 or bigger than 1. And the mu is just the center of the distribution. So for standard normal, the center is 0, but you can shift it to mu, and mu could be positive or negative. And I think a very easy way to check it is that, the expectation of x is 0. Here, the expectation of y is obviously mu, right? And the variance of x is 1. And here, the variance of y will be sigma squared. So let me just write it down. So the expectation of x is 0. Variance of x is 1. And then the expectation of y would be equal to mu plus sigma times expectation of x. And it's mu. And the variance of y, this is also a review of 108. Like the shift doesn't affect the variance, but this constant, the factor multiplier, affects the variance by being squared. So sigma squared variance of x. So that's sigma squared. And the reason for this is because the variance is itself a squared term, right? If you recall the definition of the variance. So that's why the variance will be equal to the factor squared, while the standard deviation of y is equal to sigma times the standard deviation of x. Okay, so what I'm saying is just to say that we can consider y to be a linearly transformed standard normal variable x, so that I could use this property along with the MGF of x we just derived. Okay, so we just derived, now recall that mxt is exponential t squared over 2. This is what I have. Then, based on this property, myt is equal to, this mu is my A, okay? Sigma is my B. So using this formula, I have exponential mu t times mx sigma t. Okay, I'm almost there. Last step is to plug in the form of mx. So I get exponential mu t times exponential sigma squared t squared over 2. And that's the moment generating function of a general normal variable. So you see, I saved the trouble of deriving this from scratch by doing the integration of the moment generating function. Because when mu and sigma are involved, then the integration is getting a little more complicated than what we have seen before. Because, so in this case, let me just tell you that this is the PDF of standard normal. It's simple, right? There's no sigma, there's no mu. But if for the this general normal, here the density, let me say, the density for y, let's say fy, is actually taking this form, 1 over root 2 pi times sigma times exponential to the power x minus mu squared over 2. So you are going to do the, not x, y, my bad. Y minus mu squared over 2. So you're going to do the integration for this. And you see with the sigma, with this mu here, it's a little bit, a lot more tedious work to do the integration. So that's why doing this directly is doable. We can directly derive the moment generating function of y using the density. There's no problem with it. It's just a little bit more algebra. But if we start with the moment generating function of x, which is simpler, and then do the transformation based on the property, then we can get the same result in a quicker way. So that's the goal here. And this property is very useful so that you can apply it to any linear transformation of a random variable. Okay, so any questions so far? All right, so we just talked about the first property of MGF. It's about linear transformation. All right, then let's talk about the second important property, which is about the summation of two independent random variables. So let's say that x and y are independent random variables. So maybe this is another review. So please try to remember, what do we mean by saying two random variables are independent? There are multiple ways to say it, and you can think about it for now, and I'll quickly give you the review. Okay, so there are two independent random variables with MGFs, MX, T, and MYT, respectively. Okay, then the question is, the MGF of x plus y, the sum, is, we write it again by putting the random variable in the subscript, x plus y at t. And I tell you, the conclusion is that it's equal to mxt times myt, just the product of the two MGFs. Okay, so now let's try to recall what properties we have for two independent random variables. So there are multiple ways to say it. So the first way to say it is that the probability of any joint events of the two random variables. So let's say recall independence. The first way to say it is that the joint probability of, say, x in some set x and y in some set y. So they're each in a set. So the probability of this joint event is equal to the product of each event times the probability. Okay. So this is one way to say it. The joint probability equals the product of the two marginal probabilities. Another way to say it is based on conditional probabilities. So that is, if we look at the probability that x in the set conditional on y in this set is equal to just the probability of x in this set. So which means that the conditional doesn't play a role here. It means that regardless of what values y takes, the probability of x taking a value is always the same. So this is a more straightforward way to say independence, which means that the behavior of y has nothing to do with the behavior of x. Okay, so as a result, right, the independence gives us a very important property regarding expectations. So basically, we say that for any transformation on x, so let me just say, probably let me try to use a different term. Yeah, let me see, g of x, g is some function that transforms x times h of y. These are transformations. So a result is that if you just apply any function to x and y separately, then the transformed gx and hy, they're still independent. The reason is that the randomness is carried from x and y. So therefore, you can intuitively see that the values of y has nothing to do with the values of x. Therefore, the values of hy would have nothing to do with the values of gx, right? Because the gx carries the value of x, while hy carries the value from y. So this expectation of this product under independence can be written as the expectation of g of x times the expectation of h of y. So in other words, we could factorize this joint expectation. And that's the property we are going to use here for this NAMGF. So therefore, let's try to go to the proof. Here, the proof is also just one line for the moment generating function of x plus y at t. By definition, it's the expectation of exponential t times the random variable. Here, the random variable is x plus y. And now we're going to use the fact that sum in the exponent is equal to the product of the two exponential. So I can write as exponential tx times exponential ty, right? Just the property about an exponential function. Now, independence. Because of the independence, let me just write one line. Because of independence, I can separate the expectation into two expectations. Expectation of etx times expectation of ety. And these two are exactly the definitions of mxt and myt by definition. So it's mxt times myt. And that concludes the proof. So you can see we're basically using the property or the definition of the exponential of the moment generating function as the expectation, right? And then we use the fact that this sum in the exponential function is equal to the product of two exponential functions. And then we use the independence to separate this expectation of a product into a product of expectations. And then we use definition again. All right, so why is this useful? Again, we are going to show you two examples to show that we can use this property to show that if two binomial random variables share the same p, the same success probability, then their sum is still a binomial random variable. That's the first example we'll show you. The second example we'll show you is that the sum of two Poisson random variables is still a Poisson. And we're going to show you that because of the moment generating function we derived, once we derive the sum and check the form to see it still belongs to the moment generating function we derived, then we can conclude, oh yeah, this is a negative binomial, this is a binomial, this is a Poisson. So we'll see those two examples one by one. So first example is we have x follows binomial with total n1 success probability p. Okay, and we have y binomial into total success probability p. And the key is that x and y are independent. Otherwise, we cannot use this property. Okay, so let's do the derivation. So let's recall what we have for the binomial NGF. That's what we did in the last lecture. So recall that mxt, based on what we derived, is equal to et times p plus 1 minus p to the power of the total. Okay, here previously the total was n, so we have the power n. Here we use n1 as a total, so this should be n1. And for myt, the same. etp plus 1 minus p to the power of the total, and that's n2. So now you see why having the same P would make it easy for us, because here you have the same base for the two MGF. So then the total MGF, x plus y, would be equal to mxt times myt, okay? I multiply those two things together. And because they share the same base, I can merge the two terms. So I get ETP plus 1 minus P to the power here N1 and N2. When I multiply them, and the power will be their sum, N1 plus N2. Okay. Then you compare this form to the MGF form of a binomial. You can conclude that it's the same function, right? It's the same function family. So it's just the same term to some power, same term to some power. So you can recognize that. So I'll just write it, which is the MGF of a binomial random variable. You recognize the form. And because of the form, you also know that in this MGF of a binomial random variable, the P is the success probability and the power is the total. By recognizing this, you can conclude that x plus y follows binomial distribution with total N1 plus N2 and success probability P. So this is the reason why we want to introduce the MGF, because it gives us a way to verify the distribution of a random variable. So like here, we know what's the distribution of x, which is binomial N1P. What's the distribution of y, which is binomial N2P. But we don't know what's the distribution of x and y, x plus y, sorry. So with this technique, now we are able to tell, yeah, x plus y is still negative, it's still binomial, and the total is now the total sum of the two totals of x and y, but the success probability stays as P. And intuitively, right, you can see why this makes sense. Just think about the motivation or the origination of this binomial distribution. So you can think about, I have N1 independent tosses of a coin and the success probability is P. So X is the number of heads I get. And then another person tossed the same coin independently for N2 times and count the number of heads as Y. Then I want to ask, what is the total number of heads from the two people's tosses, X plus Y? Then you can see, because it's the same coin with probability P, then it should be N1 plus N2, right? You just add up the total number of tosses and still it's the negative binomial. Does that make sense to everybody? Okay, great. I have a question in the chat box. Let's take a look. What would happen if P are not the same? So that's a very good question. Unfortunately, it's not a negative, it's not a binomial anymore. But because you can see, if this is, I change this to P1 and change this to P2, just think about it, then this becomes ETP1 plus 1 minus P. This becomes ETP2 plus 1 minus P. So when I calculate their product, I cannot merge them. So it's not a binomial anymore. At least it's not a binomial distribution we defined. Okay, so that's the first example. Now let's look at the second example, Poisson. Let's say X follows Poisson with the rate parameter lambda 1, and Y follows Poisson with rate parameter lambda 2. And again, X and Y are independent. Okay, So what is the intuition of Poisson distribution? So it is a count distribution. And also I have another chat. Okay, thank you. So it's a count distribution, right? You can consider lambda as, let me see, x, the Poisson random variable can be considered as the the count of an event, how many times an event happens. So for example, you can consider that I have a restaurant and I count how many customers I have every day. So then you can consider lambda to be like the average number of customers I have over a certain period of time. But every day, the number of customers I have can be random. Like sometimes it could be 10, sometimes it could be 12, sometimes it could be 8, but the average is 10. Let's say lambda 1 is 10. So lambda 1 gives me an idea about the average number of counts I get, right? So that's why expectation of x is lambda 1, expectation of y is lambda 2. So now let's say that here they're independent. What's the intuition? Let's say that we have 2 restaurants, okay? And the number of customers each restaurant has is independent of the other restaurant. And I'm interested in knowing what's the total number of customers the 2 restaurants have on the same day. So in this case, you see, because of the independence, then your intuition would tell me, yeah, like here, the count here has nothing to do with the count here. So then together, I should still have a Poisson, but with a rate parameter add up, right? With a rate as lambda 1 plus lambda 2. That's our intuition. And then let's verify it to see if it's true using the moment generating function. So again, we use the result we derived just now at the beginning of today's lecture. So the MGF of x being Poisson is equal to exponential to the lambda 1 times e to the t minus 1. That's what we derived in the beginning. And myt is e to the lambda 2 times et minus 1, right? And then because of independence, I have mx plus yt being the product of mxt and myt. Now I multiply these 2 terms. Et minus 1 times. Okay, now I know that with this product, I need to take the sum of the 2 powers, right? And because they share the same term, et minus 1, I can combine them. So I would get, e to the lambda 1 plus lambda 2 times et minus 1. That's it. And again, let's see whether this form belongs to the form of the MGF of a Poisson variable. And it does. It's just that, it has this form e to the t minus 1. That's the term involving t, right? The argument. And before it, I have the rate parameter as lambda 1 plus lambda 2. So again, by recognizing the form, I say which is the MGF of a Poisson random variable. So using the property that the MGF uniquely determines the distribution, I conclude that x plus y follows Poisson with rate parameter lambda 1 plus lambda 2. So I confirmed our intuition. The sum of 2 independent Poissons is still a Poisson with the rate parameters added. Okay, so is everyone okay with what we have so far? So we apply the second property to derive the distribution of a sum of independent variables. So we have done binomial and Poisson, which are 2 discrete distributions. Now let's do a continuous one, the normal distribution. All right, so example 3, let's say we have X following normal distribution with mean mu1, variance sigma 1 squared. Okay, so this is something I want to make just clarification. So in this class, we will put the second argument of the normal distribution as the variance, not the standard deviation. So that's why we have the square here, sigma 1 squared. And y normal with mean mu2, sigma 2 squared. Okay, and again, x and y independent. So we'll do the sum. Okay, what's the distribution of the sum? So we actually, a very important fact about normal variable is that here they're independent. So things are easy. So we know that their sum, we'll see that it's still a normal distribution with a mean add up, with the variance add up. That's a very nice property about normal variables. And we will try to verify that using the moment generating function. But intuitively, you can see why. So like, think about, you have two random variables that are both normally distributed and they have different means, right? When you add them up, then the sum would have the mean that's equal to the sum of the means, because expectation of x plus y would equal to the expectation of x plus expectation of y. That would be mu1 plus mu2. And regarding the variance, you can see that x has this degree of variance sigma 1 squared, right? And y has this degree of variance sigma 2 squared. But when you add up, the randomness would also add up. So the sum would actually have a larger degree of randomness than individual one has. So it makes sense to think, yeah, the sum will have a bigger variance, and that bigger variance turns out to be the sum of the variances. And that's another important property we have for independent random variables. So that will help anyway. Let me just write it here. So for independent x and y, we always have these two properties. So that is variance x plus y would equal to the variance of x plus the variance of y. Okay, this is just a fact that holds for independent x and y. And regardless of the dependence, I'll just say for any x and y. So they could be dependent, they could be independent. The expectation of their sum is always equal to the sum of their expectations. So this expectation relationship doesn't require independence. It just holds in general. This is just because we could put expectation inside each term, inside the sum. This is just by the definition of expectation. If you think about it as a sum or as an integration, we will have this. Okay, so anyway, so you can see that what we can know for now is the expectation of x plus y here would be equal to mu1 plus mu2. And the variance of x plus 1 here would be equal to sigma 1 plus sigma 1 squared plus sigma 2 squared. But the question is it normal? Is x plus y normally distributed with this mean, with this variance? That's our question, right? So knowing the mean and the variance alone will not tell us whether the distribution is normal or not. These are two questions. So we have to rely on the MGF to help us check it. Let's first take a look at the MGF of x and MGF of y based on what we just derived. So recall that MXT is equal to e to the mu1t times e to the sigma 1 squared t squared over 2. What we just derived using the first property of MGF, like the linear transformation property. And MYT equals e to the mu2t times e to the sigma 2 squared t squared over 2. Right? Now let's combine them. So the MGF of x plus y at t is just their product. And you can clearly see that by combining the similar terms, right? The term involving t in the exponent, these two will be similar. I can combine them. These two involving t squared are similar. I can combine them. So by simple algebra, I can have the first term combined as mu1 plus mu2 times t, okay? And the second term, exponential, I can have sigma 1 squared plus sigma 2 squared times t squared over 2. Right? It's just combine the same similar terms. And now you see by comparing this form of the MGF of x plus y to the MGF of a normal variable we derived, you can recognize that this is still the MGF of a normal random variable. With the mean is just the coefficient of t. The variance is the coefficient of t squared over 2. So then we recognize, oh yeah, the x plus y mean is mu1 plus mu2. Variance is sigma squared, sigma 1 squared plus sigma 2 squared, which is the same as what we derived using the mean and variance formulas. And this gives us that it's a normal variable. So that's why we conclude that. So which is the MGF of a normal random variable. Okay, so we conclude that x plus y follows normal distribution with mean mu1 plus mu2, variance sigma 1 squared plus sigma 2 squared. That's it. So far we have seen 3 examples about deriving the distribution of a sum of independent random variables. So just to summarize, the sum of 2 binomial random variables with the same p is still a binomial. It's still a binomial with total as the sum of the 2 totals. And for the sum of 2 independent Poisson, is still a Poisson random variable with a rate parameter as the sum of the 2 rate parameters. And finally, the sum of 2 independent normal random variables is still a normal random variable with the mean as the sum of the two means and the variance as the sum of the 2 variances. And the MGF is a useful tool for deriving this. Okay, so finally, let's see a challenging example. So this is a quite interesting example for us to actually, let me see. Sorry, I think I'm not there yet, like that. So yeah, we'll do the challenge later. But actually, so for now, let's generalize the distribution. So the result, the property, to be the sum of not just 2 random variables, but in random variables. Okay, let's do this. So now let's say that we have x1 to xn are IID. Now we see this term again. What it means? It's independent and identically distributed. So they are from the same distribution, but they're all independent of each other. Independent and identically distributed random variables. Okay, so now the question is, what is the MGF of their sum? So now I write as I from 1 to n. I take the sum of all of them. So it's not a sum of 2 random variables, but a sum of n random variables. So just quickly think about it. We should be able to do it given what we have seen before, right? We can use the independence. That's one way. We can use the independence and the definition of the MGF to write the MGF of a sum as the product of individual one's MGFs. That's one possibility. Another possibility is that we could use the fact of the sum of two random variables. So we can write this as the x1 plus I from 2 to n. And then we can separate those two terms. And for the I from 2 to n, I can write as x2 plus I from 3 to n. I can do that sequentially. But anyway, you see that here I can have m, the total, this MGF, written as mx1t times mx2t times mxnt. Okay, that's just based on independence. Okay, using independence, I can get here. And you can see I didn't use the identically distributed condition yet. So being identically distributed, it actually means that all the x1 to xn are from the same distribution. And from the same distribution, it means that they have the same MGF, right? Because we say there's a unique relationship between MGF and distribution. So being identically distributed, it means that these are all the same. Okay, so it tells me mx1t equals mx2t equals mxnt. So therefore, I could just denote it as one term, mxt. Okay, there's no need to differentiate them. Because of this identical distribution, they are just the same term multiplied by n times. I just write mxt raised to the power n. That's what I have for this IID result. The sum of IIDs has MGF as the nth power of each random variables MGF. So the power is just the number of random variables I have here. And so later we will see that we usually use this n to denote our so-called sample size. By sample size, it means that we have a sample of n random variables. So let's just imagine that you have, say, you perform an experiment independently for n times, and each time you get one measurement. So x1 is the first measurement, xn is the nth measurement. So when you take your set of n measurements together, you call that as your sample. And this n, the number of repeats you performed, is the sample size. So intuitively, you can see the larger, the better, right? So we will see that later. But for now, we're just using this probability formulation to say are them as n random variables. They are independent of each other because the value x1 takes has nothing to do with the value x2 takes, has nothing to do with the value xn takes, but they all from the same distribution. So that's why we say it's identically distributed. Okay, so now seeing this result, right? Let's take a look at what if we have x1 to xn for IID from a normal distribution. Let's see this. So then recall that for each of them, the mxt, the moment generating function, is e to the mu t times e to the sigma squared t squared over 2. We just saw this. So now, using this result we just derived, then the sum MGF will be the power of this, right? And you know, this is another nice property about exponential function. If we raise it to the power n, the power will be multiplied into the exponent. So it's equal to n mu t times e to the n sigma squared t squared over 2. Then from this form, we can recognize it's still the MGF of a normal distribution. So we know the sum would follow a normal distribution with mean as n mu, right? The mean is the coefficient of t. The variance is the coefficient of t squared over 2. Variance is n sigma squared. Okay, so I think I should stop here. This is a generalization of the sum of n IID, not just the sum of 2 random variables. So next time when we come back, we will do a challenge problem, which will actually use something called the Tower rule for calculating expectation. So let's say if you have 2 random variables in your expectation, you can put a conditional on 1 random variable to take care of one first, and then consider the other. So what is the IID? Is the independent and identically distributed. So you will see this term again and again in mathematical statistics. Okay, so I'll stop here. And if you have any questions, you can stay in the Zoom and ask your question. Otherwise, well, I'll see you on next Monday. I think so. I think I'll assign the first homework today. So, and it will be due in a week.